So, welcome back friends to another lecture on quantum field theory and quantum entanglement. In the previous lectures what we have seen is how to quantize the photon field. We saw it is quite complicated, the quantization of the photon field. Okay. Of the photon field, we have seen the quantization in two different ways. One is through we had to fix a gauge because there are large more number of degrees of freedom compared to meaning compared to the number of degrees of freedom the field has. So, the physical degrees of freedom and the number of degrees of freedom which the field has do not match. So, we had to fix a gauge, and that is the only way we can really proceed further. So, we had considered two particular gauges. Essentially, one is a Coulomb gauge and the second one is the Lorentz gauge. As you know, the Coulomb gauge you can actually work with directly the physical degrees of freedom, and we have seen that using the physical degrees of freedom you can go ahead and quantize the thing, but it is not very convenient because Lorentz invariance is not manifest. Okay, no manifest Lorentz invariance. Okay, and this gauge also has problems as we go into higher and higher orders in computation. Okay, manifest Lorentz invariance, and it also meaning because you do not have manifest Lorentz invariance, it to keep track of all the calculations and everything becomes much difficult. Okay. So, if you are computing things, if we need something which has manifest Lorentz invariance, that is the reason why we choose Lorentz gauge, but then it has its own problems, like for example manifest Lorentz invariance. So, it has manifest Lorentz invariance, but it does not really have, it has other theoretical issues like states with negative norms, which are unphysical clearly essentially. But then we had a trick in the Lorentz gauge which is called the Gupta-Bloiler. So, Gupta-Bloiler trick through which actually we can throw away the unphysical states essentially, and we impose some condition like something like psi plus acting on the vacuum should annihilate essentially. Okay. So, the annihilation operator has a very specific meaning directly on the Hilbert space essentially. So, we went to this entire detail in the last few classes essentially. So, we will now today move to studying interactions. Okay, before I go further, we also looked at Feynman rules further in the Lorentz gauge and in for the photon field. In particular, we looked at the Feynman propagator of the photon field in both the gauges. Very good. So, today we will continue with interactions. So, the interactions we will be considering are between fermions and vectors and scalars and vectors. Okay. So, let us look at the first case. Essentially we will start with the first case. So, in the first case when we studied the Dirac equation essentially or the Dirac field, we looked at the bilinear covariants So, we looked at the bilinear covariants and then we had the pseudo scalar, the scalar interactions which we call the Yukawa interaction psi phi. So, these are varieties of Yukawa interactions which we studied. The other next bilinear which would come is something which couples directly to the vectorial current of the Dirac field. Okay. This is precisely what we are looking at. So, to make a Lorentz scalar of the vectorial current made up of two fermions, you need another vector and that vector is the photon field essentially. So, that vector is the photon field and so this is the interaction we will study today essentially. So, the interaction we will study today is a current like interaction So, this will be a mu the photon current interacting with the Dirac current. So, this is the interaction I want to put it in my Lagrangian essentially. So, I also need to give some coupling constant to this essentially, let me give it some coupling constant. So, with this I want to write the full Lagrangian. So, the full Lagrangian would be L is equal to the kinetic terms for the Dirac particles which are essentially I del slash minus m psi, which let us take them to be let me say specify what is psi is. The kinetic terms to the photon field which is given by this F mu square, and finally the interaction between the electronic current and the Dirac current and the photon field essentially. You see that this is the only way which can couple to it essentially the photon field. You can always put a gamma phi, but I will see later that this gamma phi only works in a chiral theories essentially. It does not QED is a vectorial theory, so it couples only to vectorial currents essentially. Okay. This entire Lagrangian is known as the QED Lagrangian. Okay. It is known as the QED or quantum electrodynamics Lagrangian. Okay. This is the quantum electrodynamics Lagrangian. So, it is a theory of just electrons and photons. Okay. QED is a theory of just electrons and photons. Okay. So, this is a theory quantum electrodynamics. This is a theory of electrons and photons. Very good. So, this is very nice essentially the photons couple vectorially to the electronic current. So, psi here, to be more specific, I can just put it as electrons. Okay. And this is the electric charge coupling constant essentially associated with the coupling constant. You see the theory is extremely simple. You have the kinetic terms of the photon, you have the kinetic terms for the electron, and then you have the only one interaction term. There is only one interaction term between the electrons and photons. So, it is extremely simple and it is almost like the Yukawa interaction, except that now you have a vectorial interaction essentially and you have the kinetic terms for the photons. Now you can let us look at the what are all the possible symmetries of this Lagrangian. So, the first one is that there is a continuous symmetry. So, continuous symmetries, let us look at continuous symmetries. Now, the field psi E appears always as a bilinear, you see that it always appears as a bilinear. So, that means meaning there is psi bar psi, there may be a derivative of gamma mu in between. Gamma mu is a constant matrix, I del slash m also is a constant matrix essentially. The p slash, okay, yeah, p slash is there, okay. Now what happens is if I rotate psi E fields by an arbitrary phase, the Lagrangian is invariant. Okay. The Lagrangian is invariant if one rotates the psi E field by an arbitrary phase. So, psi E prime goes as psi E, okay, e power I alpha q some alpha p psi E. Now, psi E bar prime is equal to e power minus alpha q psi E bar. Now, you see that immediately that the entire Lagrangian is invariant under this transformation. So, if you shift psi E to psi E bar, replace psi E by psi E bar, psi E prime, the Lagrangian is invariant. So, if I replace psi E by psi E prime, the Lagrangian is invariant, I mean in the sense, or you can do the other way around, psi E is equal to you can get what is psi E and psi E prime and the Lagrangian is invariant. So, it means that there is a continuous symmetry in terms of the internal symmetry, continuous internal symmetry under which there is the Lagrangian is invariant, which by itself means that under Noether's theorem there is a conserved charge quantity, let me call it as charge and current. So, there is a conserved charge and current and which has the same form as this what we have written essentially psi bar gamma mu psi. So, under the Noether's theorem there is a conserved charge and current. So, because Noether's theorem only works for continuous symmetries and the converse may or may not be true, but so the okay. So, but there is always a conserved charge associated with a conserved symmetry essentially. Okay. So, this in this case what is a conserved symmetry? The conserved symmetry is this arbitrary phase transitions which are global and the conserved current and conserved charge are nothing but the electric charge and current. Okay. This is very crucial, and this is actually a very important point essentially, that the one of the first transformations you can think about, or the symmetries essentially associated with this Lagrangian, is a continuous phase transformation. Now this arbitrary phase transition, now you remember this is some number, this is some parameter, some field, scalar field. Now this is this is not a scalar field, this is some number, this is all arbitrary parameter, arbitrary. Now it is a global parameter, it does not depend upon, or which does not depend upon space time. That means it does not change at every space time point essentially. For all practical purposes you can forget about this Q, okay. It does not really matter because we are only in a theory of one electron and one photon, okay. So we can just put it I alpha, and then electric charge can be normalized to 1, and so this will just become some arbitrary phase essentially. So there is a conserved current and conserved charge, and which are essentially electric charge and electric current. Now now what happens, okay, this is one of the first continuous meaning conserved quantities, symmetries of this Lagrangian. Actually the Lagrangian is much more powerful in the presence of interactions. Has a much bigger symmetry. In the presence of interactions. So what I am trying to say here is this conserved current and conserved charge exist even if there are no interactions, okay. So the Noether's theorem holds and everything. So you have so this arbitrary space rotation, it will always hold even in the presence of even in the absence of interactions, also in the presence of interactions. But in the presence of interactions there is a much stronger symmetry which is valid essentially. So in the presence of interactions it is not just a global phase rotation which is valid, but you can also have local phase rotations. So in principle you have psi e prime e power alpha of x times q psi e. Now what did I do? This alpha I made it into a space time quantity, okay. So essentially I am putting here a scalar field, a function of x, alpha of x, and q is your charge essentially, charge, electric charge. Under these transformations I demand that the Dirac Lagrangian should be invariant, okay. Okay, let me write it in this manner. So we want the Dirac Lagrangian to be invariant under this thing. So what we do, so let us start with the Dirac Lagrangian. Now psi, so I want to substitute psi to psi e prime, okay, with the same transformation properties. Now if you see, there is a term which has a derivative here, the derivative will see the alpha of x, it will also act on the alpha of x. So what happens if I have psi e prime is equal to e power I alpha of x times q. So del psi is equal to del psi e prime goes to del psi e prime is equal to, okay, so is equal to e power I alpha of x q del of psi e prime, okay, till first so fine, then plus psi e prime times del I, okay, I alpha del alpha of x I q del alpha of x. Okay, psi prime del alpha of x. So because this extra term arises, an extra term arises, now you can observe this in interaction theories. Now if you, okay, now suppose if you have a new field, so what is del mu, del slash is equal to del mu a mu, so this is del mu, this is del mu. Now suppose if you have a field a mu which also transforms under this local gauge transformations is equal to a mu plus I e q del mu alpha of x, okay. If this also transforms in this particular fashion, okay, then together you can make the entire thing okay, gauge invariant essentially, or this transformation is also called a gauge invariant transformation. Together this entire thing will become invariant, but this requires in the presence of interactions. This only happens in the presence of interactions. In the absence of interactions, you cannot have this kind of a local transformation essentially, because the local meaning this local transformation will not be valid because you have this extra term which is del mu alpha of x. If in the presence of interactions, what you can demand is the interactions will bring in an extra term a mu, but this a mu transforms in this particular fashion, and so this extra piece I can cancel with the term of the at the term which is just generated by the del. Okay, now you may not get the entire meaning. Let me convince you how this happens essentially. Let me just tell you how it happens. So now what the plan to do, the way to do is essentially just to say del mu is moved to something like a covariant derivative del mu plus I e a mu, okay. That means you are introducing interactions in with a minimal coupling way essentially. Now when you do this, you will immediately see what is happening to the Lagrangian, okay. Psi bar I del mu slash minus m psi minus 1 by 4 f mu nu f mu nu. Let me expand this. Psi bar I del mu plus I e mu minus m psi minus 1 by 4 f mu nu f mu nu. This is equal to psi bar I del slash minus m psi minus 1 by 4 f mu nu plus I e psi bar gamma mu psi a mu. Okay. So, you see that this is the same interaction term which we have written earlier. This is the same Lagrangian where we introduced okay, where we introduced the interactions as a vector vector interactions essentially. So, we are getting the same Lagrangian, but this time how did we get it? We are getting it by demanding that there is a symmetry, okay, there is a symmetry associated with the psi fields, okay, associated with the psi fields, that they are invariant under this symmetry at every space time point in nature. Okay. They are invariant under every space time point in nature. So, this is the symmetry we are looking at. Okay, this looks ugly. Okay. Okay, let me try some. Okay, this is better. So, this is the symmetry we are looking at, and so this symmetry automatically, by imposing this symmetry, you are getting your interactions, or in other ways you are trying to understand your interactions in terms of some symmetry properties essentially. Now, how does this work? Okay. So, I still not convinced you that how does it work, meaning, so I say that suppose if I psi goes to psi prime is equal to e power I alpha of x q psi. So, we have seen that there is an extra term coming from the first set of equations. So, the first set of equations give me this extra term. So, this thing, let me call this as term 1, term 2, term 3. So, term 1 gives me the term psi bar I del slash minus m psi prime. So, it gives me the same thing, plus there is this term which comes with the term 1. So, it gives me this term I e psi bar del mu alpha gamma mu psi. Okay. This is the term which gives me extra essentially. The second term term 2 is del mu a nu minus del nu a nu. Now, I also demand a nu transforms now you can see immediately that a mu is invariant under this transformation. So, you can always write it down. If we put a del mu del square alpha and then del mu del square alpha, the del square is symmetric. So, this goes cancelled. So, this is equivalent to del mu a nu prime minus del nu prime a mu. So, each term, okay, is invariant. So, this is one of the homeworks essentially. You explicitly work it out and show that this is invariant. What happens to the third term? The third term automatically gives me this term with an opposite sign which will cancel this extra term. E gamma mi plus okay, which will cancel. This should be all size, okay, sorry, which will cancel with this term, which will cancel this term. So, I want you to check this algebra again, essentially you guys check this algebra one more time. Okay. So, this will cancel, and so term 1 plus term 2 plus term 3 shows us that the Dirac Lagrangian with interactions is invariant under local gauge transformations is goes to so it remains invariant. Now, how did we get this invariant Lagrangian? This is the same Lagrangian, but with the ordinary derivative replaced with del mu, and under this is true if we have interactions, and this Lagrangian is invariant under which we call as, so these are called local gauge transformations. Okay. So, we have local gauge transformations. So, these local gauge transformations is also a local symmetry. There is no corresponding Noether's theorem for local symmetries essentially. So, the Noether's theorem works for global symmetries. So, for local symmetries it does not work, but there is a in this particular case of QED there is a corresponding conserved charge, which is the electric charge, which is conserved locally at every space time point, and at every space time point, because we are demanding the symmetry to be conserved, you always have a gauge boson associated with it, which is nothing but your photon field, and this photon field is also called as the gauge boson, essentially is also called as the gauge boson, and this is the full QED Lagrangian written, understood and written in terms of the symmetries, internal symmetries essentially. So, you see that it is invariant under these internal symmetry transformations, okay, written and understood in terms of this thing. So, this shows you that there is a conservation law, okay, which tells you that this is a particular very peculiar for QED, in general it is not always true, that the local case also has a conserved charge, which is essentially associated with the electric charge and electric current. Okay. So, let me stop here and then we will continue with the other symmetries associated with the fermionic QED, and then we will start looking at simple process in QED. Okay. So, let me stop here. Thank you.